Marilyn.
Hey Polo, how are you?
Good, how are you?
Pretty good.
What you working on?
Oh, I'm just coloring. I'm trying to de-stress from physics because that class is so hard.
Oh, you're telling me. Have you been working on your interpretation of ray diagrams tutorial homework?
You know it.
Oh God, I know, it's so difficult.
Honestly.
So what's your picture?
Oh, I was just drawing the sun.
Oh, that's nice. But there seems to be something wrong with your sun.
What are you talking about?
I mean, aren't you in physics? You should know that the sun is not yellow.
The sun is definitely yellow. Have you ever been outside?
Of course I've been outside. I don't live under a rock.
Dependent on the medium through which it's traveling. If the light changes mediums while going at an angle, its direction will also change. We can find the new speed of the light using the equation the velocity equals the speed of light divided by the index of refraction. We can also find the new outgoing angle using Snell's law, using the incoming angle and the two indexes of refraction. Now there are many types of light rays. They're all covered by the electromagnetic spectrum. It goes from radio waves that we hear about all the time, all the way to gamma rays, which can be used in medicine. The visible spectrum comprises the light waves that we interpret as visible colors. So red, orange, yellow, green, blue, indigo, and violet all have different wavelengths. Now the angle of refraction is dependent on the wavelength of light. So even though a blue light ray and a green light ray enter at the same angle, their outgoing angles are going to be different. This lets us take white light, which is a combination of all the visible light rays that we can see, and break it up into its components.
Okay, this is really cool and all, and I think I understand where you're coming from. But how do I know that this applies in the real world?
Well, let's look at an example then.
Using a spectrometer, we're able to see the distinct wavelengths coming from a light source. So, from this white light source, we should be able to see what specific wavelengths are being emitted using the Ocean Optics software.
Our results from the spectrometer using white light demonstrate that white light is not a single wavelength, but rather a combination of all the visible wavelengths. Instead of having one distinct peak, we have a flat plateau from about the 400 nanometer range to the 700 nanometer range. And this encompasses all of the visible light that our eyes are able to interpret. We are able to use instruments such as prisms to separate out these wavelengths into their distinct color components.
So we have a diffraction grating that is able to take the white light coming from the lights around us and break it up into its visible components. So we can see that it follows the spectrum of the visible wavelengths of light. We can see the red light to the yellow to the green to the blue. And this is because it's separating out those wavelengths on the distinct angles of refraction they have in a different medium. While this phenomenon is great for explaining how rainbows form in the sky, or why sometimes you see mirages if you're in the desert, or why stars in the night sky seem to fade in and out, it's not all entirely useful to explain why the sun is yellow. For that, we have to look at a different property of light that depends on wavelength.
In order to understand why the sun looks yellow, we have to consider scattering throughout the atmosphere. So, molecules and gases in our atmosphere, they scatter rays of light from the sun. According to Rayleigh's equation, the intensity of this scattering is indirectly proportional to the wavelength.
This means that the smaller wavelengths like blue, indigo, and violet are more likely to be scattered. This explains how our atmosphere protects us from ultraviolet radiation, which has an even smaller wavelength than violet light. That leaves the green, yellow, orange, and red wavelengths coming down to Earth for us to interpret what our sun actually looks like.
And this is also why we interpret the sky blue, because blue scatters.
We can use a glue stick to model how scattering happens in our atmosphere. When the light initially enters the glue stick, it appears white. But as we move further down the length of the glue stick, it gradually changes color, becoming more reddish in tone at the end. This is because more of the shorter wavelengths are being scattered at the beginning, so our blue, indigo, and violet, but as we move further down the glue stick, even the greens and the yellows are being scattered. So at the end, really all we're left with is the red wavelengths of light, which are the longest. To understand this on a larger scale of how it looks in our atmosphere, let's look at a different example.
So to model our atmosphere, we decided to fill a tank with water.
We have a flashlight on one side to represent the light coming from 93 million miles away from the sun to the earth. To represent the nitrogen, oxygen, and other gas molecules in the atmosphere, we're going to use powdered milk, which will scatter the light in the same way that the gas molecules do in our atmosphere.
If we view the tank from the side, we can see how it appears similar to what we observed with the glue stick. We see white light coming into the tank, but by the end, it appears more in an orangish tone. If we view the tank head on, we can see how this appears similar to our sun. It's a yellow tone, even though we know it's white light coming in. If we add more powdered milk to the water, it becomes even more red. This is similar to what happens when pollution adds more molecules to our atmosphere, causing more scattering, or what happens when the sun is setting and so it's coming in at an angle that causes it to go through more of our atmosphere.
Something in the water. Oh, there must have been something in the water.
Okay, so I understand now how light scattering could cause something that's coming into the atmosphere as white light to appear yellow to us. But how can you be sure that the sun is actually emitting white light?
To figure that out, we're going to have to talk about black body radiation. Black body radiation is the idea that all materials that are over the temperature of absolute zero are emitting some amount of radiation. The amount of radiation and the wavelength is dependent on the temperature of the object. So for our sun, the wavelengths it emits are dependent on the temperature it's at.
As we heat the wire, it changes the frequency of light that it's emitting, going from infrared to red to orange. This is because as the temperature increases, the black body radiation emitted goes up in frequency. If we were to continue heating the wire, it would eventually emit wavelengths in the blue end of the spectrum.
A similar thing is happening with the sun. Because of its high temperature, it's emitting electromagnetic radiation across the spectrum. The ones that primarily affect Earth are the infrared, the visible, and the ultraviolet radiation. Because we know it's emitting light in the infrared and the ultraviolet, we know that it's emitting wavelengths across the visible spectrum, from red all the way to violet. This means that the light that's reaching us that we can see and interpret is white light.
So through all of our experiments, have we convinced you that the sun is actually white and not yellow?
You know, yeah, after doing all of that and seeing all of your guys' explanations, I do agree with you that the sun is actually white. What really sucks is that now I'm going to have to come up with a new way to de-stress after physics, because drawing just really isn't going to work anymore.
This should put in the credits. Now out of all the women in the place, you got me staring at your pretty face.